Hello, everyone. My name is Guy Rushanek, and today I will be going through and lecturing Chapter 4.1, Basic Concepts of Probability. So today, let's go through some objectives. We're going to discuss the role of probability in statistics and how statisticians interpret probability for us to be able to solve a problem. Then we're going to go through some definitions, which we will need to understand the formulas and how we can calculate probability. Then we're going to talk about significance results and how that prompts an explanation for probability. And then we're going to go through some example problems together. So let's get started. Role of probability in statistics. Probability plays a central role in the important statistical method of hypothesis testing, introduced later in Chapter 8. Statisticians make decisions using data by rejecting explanations based on very low probabilities. Again, the English and exact wording on this is very important. We're going to discuss this a little bit later, but it's important to understand that all hypothesis testing allows us to do is either reject a probability of something happening or fail to reject an explanation of something happening. And we'll dive into that deeper so you all will understand that a little further. So let's go through some definitions. First of all, I want you all to understand an example. So let's just say you roll a die, right? And we're going to talk about the probability you get 1, because we all understand very simply the probability is 1 out of 6. So an event is any collection of results or outcomes of a procedure. An event would be rolling die. A simple event is an outcome or an event that cannot be further broken down into simpler components, which means a lot of times you can say, what are the odds that I land a 1 3 times in a row? Well, then it's not a simple event because you have to base it on the other 2 roll attempts. The sample space for a procedure consists of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. So the sample space for rolling a die would be the results anywhere, any number, 1 through 6, right? Any integer. And then the complement of A, denoted by A bar, which this symbol is identified as the complement, consists of all outcomes in which an event does not occur, right? So if there's a 1 out of 6 chance that you roll a 1 when you roll a dice, then there's a 5 out of 6 chance, and that 5 out of 6 is the complement of event A. And it's important to understand that the complement of A and A itself must add up to 100% likely probability of it happening, right? Because if you roll a die, you have to have some sort of result. So let's go through some ways in which you can approach probability. The probability of an event is a fraction or decimal between numbers 0 and 1. The probability of an impossible event is 0, right? So getting 19 when you roll die is not likely and actually impossible to happen, right? So it's 0 out of 6, or excuse me, 0 out of 1 in terms of converting a probability into a number, into a decimal, and then the probability of an event that is certain is 1, right? So rolling a dice and landing anywhere from any integer 1 through 6 is certain. So there's a 100% chance of that happening, or we can convert that to the decimal 1.0. Then the notion P of A is interpreted as the probability of event A, and then P of A bar is the probability that A does not occur. So let's look at the classic approach to probability. If a procedure has n different ways in which a simple event are equally likely, and if an event A can occur in s different ways, then the probability of A is the number of ways in which A can occur, which is represented as s, over the number of different sample events, which is n. Another way we can look at it, right, is interpreting A, B, and C as specific different events. So P of A denotes the probability of event A occurring, as we already said. The following three approaches are finding probability result in the values between 0 and 1, as we discussed, because the possibility of something happening 100% is interpreted as the number 1, and something happening 0% likely is represented as the number 0. So it shows the possible values of probabilities and the more familiar and common expressions of likelihood. So we can also use this way to interpret, which is not the same as S over N. This time we can calculate the probability of A by placing the number of times A occurred over the number of times the procedure was repeated, right? And this is referred to as the relative frequency approximation of probability. So now let's look at significant results and how it relates to probability. If and under given any assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less or significantly greater than we typically expect without assumption, we conclude that the assumption is probably not correct, right? So let's talk about significantly high number of successes as compared to significantly low number of successes. X successes among N trials is significantly low if the probability of X or fewer successes is unlikely with a probability of 0.05 or less. That is, X is significantly low number of successes if P of X or fewer is less than 0.5, right? And this would be in this category when you graph the results that this would be starting to get towards extremely unlikely and actually impossible. So we're going to look at an example problem now. Among 20 births, 20 girls is significantly high because the probability of 20 or more girls happening out of 20 births is 0.000954, which is less than or equal to 0.05. And this allows us to understand that because the probability of getting, if you analyze 20 random births, let's say at a hospital, the probability that 20 of them will be girls, and therefore we can conclude something along the lines of, right, that a girl is more likely to occur. We understand that we can reject this claim because we understand that the significant probability of this happening is below 0.05, right? And then another way, right, if we find that 12 of the 20 girls are born, 12 of the 20 births, are girls, then that number, the probability would be converted to 0.251722, which is greater than 0.05. So then it doesn't appear that we can reject the claim that girls are more likely to be born than boys, right? And then this is an easier way for all of us to be able to visualize this. If this is the occurrence, then we rejected as a possible explanation that gender selection method appears to be effective. And then if it's not, we do not reject and cannot conclude gender selection method is effective, right? Now let's discuss some practice problems together. So we're gonna have three sets of problems. The probability that when we roll a 6-sided die, the outcome is 4. The probability that when we flip a coin, the result is tails. And the probability that when a 6-sided die is rolled, the outcome is 19. As we mentioned before, there's a few different ways to find the probability of A, which is the designated event to occur, right? So we're going to look through S over N, the number of ways A occurs, over the number of different simple events. So let's break it down so we all can understand this in a more practical use. Let's first examine how many 4s are on a 6-sided die. It's a simple answer. It's 4. Sorry, it's a trick question. It's actually 1, right? There's only one 4 on each die. And now we're going to ask how many sides are on the six-sided die. That should be well explained. There are 6 sides. So now we divide the probability, right? 1 over 6. And 1 over 6 is equal to 0.167. So we can thus conclude the probability of rolling a 4 on a 6-sided die is 1 out of 6, or 0.167. Now let's look at B. Find the probability that when a coin is tossed, the result is tails. How many tails are on a coin? Well, there's only 1. How many sides are on a coin? Right? To be able to flip is 2. And then we divide the probability. Very simple. Probability of tails is 1 over 2. So we can conclude that when tossing a coin, the probability is 1 over 2, or 0.5. Now let's look at C. Find the probability that when a 6-sided die is rolled, the outcome is 19. So the first question we ask ourselves is how many 19s are there on a 6-sided die? We understand there are 0, right? So now we ask how many sides are on a 6-sided die, as we mentioned before, and as mentioned in the question itself. There are 6 sides. So now we do some very complicated division and conclude that 0 over 6 is 0, and therefore the probability of rolling a 19 on a 6-sided die is 0 out of 6, or 0. Thank you all very much for listening to this presentation. I hope you learned something about probability, and I hope you all have a great day.